So in the last class, we talked about organizing data. And I think the main takeaways of the last class were the numerical measures that we use to organize data: mean, median, mode, range, and so on. What I would like to focus on today is presenting data. So we already talked about how to organize our data, how to organize our measurements, our observations. But now I want to talk about how to present them, because the way you present them, of course, is going to play a big role, right, in how your audience, your readers, can interpret the data that you send them. So today's focus will be in presenting data. A lot of you may think that presenting data is just an arbitrary step, right? It's just something, just one of the many steps of statistical analysis. However, we need to understand that how we present our data will ultimately influence how our data is interpreted. So this is why it's very important for us to have a good background, a good preparation in presenting data, so that we will be able to understand how our audience can interpret it. Of course, you already know that this is where the politicians, the news anchors, and other media magnates thrive, right? This is their field of this is their comfort zone, to be honest, right? This is presenting data is a very powerful tool, right? Because it does give an unsuspecting or uneducated audience, or even an educated audience, it does serve to sway their perceptions in several different ways. In the chat, we have a message: without properly presenting data, it kind of makes gathering the data useless. So that makes sense, and that's absolutely right. I completely agree with that statement. So the field of statistics that deals with presenting data is called descriptive statistics. So you'll read in your book, we have a chapter called descriptive statistics, which is the focus of this week or of today. And you'll find statisticians that consider themselves to be descriptive statisticians, right? Now, I think any statistician should know how to present data. However, there is a certain art that comes with it that requires a bit of extra studying or extra practice in order to be good at. So let's begin by talking about an example, a real life example. I decided to name this example Statistics in Serial Killers. So you may have heard of Harold Shipman. He is known as the most prolific serial killer of our time. And if you haven't heard of him, that's fine. Just to give you a little bit of background, Harold Shipman was a family doctor in Manchester, that's in the UK. And he murdered his patients by injecting them with an opiate overdose. So he was a doctor who would inject a lethal dose of some type of morphine into his patients and then murder them. After one greedy mistake, which was forging a victim's will in order for him to get some money, so he killed someone, tried to change the will so that he would get some money, and that raised suspicions. An investigation was started, and it was found that he had been retrospectively changing patient records. So after a patient would die, he would change their records to make them appear sicker than what they were. That way, that would explain their deaths. Of course, with technology, everything, right? Everything leaves a trail, including when he actually changed their records. So the investigation was able, or the investigators were able to determine that he was changing his patients' records after they had died, after the fact, just to show that they were sicker and that they were, in fact, about to die anyway. So this, of course, raises some suspicions. Okay, he's changing records to make it seem that they're gonna die, and then they die, or after they die. Therefore, 15 of his victims were exhumed, and after a study, they were found to have lethal levels of diamorphine. He was tried and found guilty of the 15 murders in 1999. So that's the information that we know so far. Doctor who would inject his victims, or who would inject his patients with a lethal dose of diamorphine. They would die. He would change their medical records to make it seem that they were going to die anyway. They were very sick. 15 of his dead patients were exhumed. It's actually very common for cremation is actually very common in the UK. So it was it was only a small number of patients that were able to be studied, right? Those that had not been cremated. And the investigation found that he had, in fact, murdered these 15 patients. Now, my question is, how many people did the doctor kill? And for you to think about it for a second, you can discuss it with me or with your classmates, but try to get an idea, okay, of how many patients did he actually kill. He was tried and found guilty of 15 murders from 15 bodies that were exhumed and that were studied. But now the question we want to answer is, how many patients did he murder? Any ideas? If you're a forensic investigator and you're asked this question, Ramtin, ha ha ha. Milton says he went 15-15. Okay, that's an interesting way of putting it. Can you repeat the numbers once more? Yeah. 15 of his dead patients were exhumed. In other words, they were, well, I guess exhumed, right? Unburied. And their dead bodies were studied, and he was found to have murdered all 15 of them. Now, the question was, how many of them did he actually murder? So if you're a forensic investigator and you're asked this question, what do you think we need to know, right? What do we need to look at? What do we need to study in order to know the number of patients that he murdered? He wasn't speaking, so there's no, well, let's just beat it out of him. And then a lot of his patients had been cremated, so there's no studying their bodies. So what would you do in that case? Okay, so Milton has a good point. We would have to know when his patients started dying abnormally. I think that's a good way of looking at it. Bailey says that we need to search the records for his total number of patients who died. And Rampton says probably go back and see what medications he used to give people. I think all those are very, very good answers, right? Are very, very good ways to start investigating. Interestingly, this job was given to statisticians. And David Spiegelhalter, who wrote The Art of Statistics, was one of the statisticians tasked with solving this problem. A couple of additional comments. I'm going to read them from the chat. It says, I'd assume some of the deaths from the meds might not have been murdered. What's the percentage of those kinds of deaths that happen otherwise? That's actually a really good point, right? We're thinking, well, instead of just looking at his patients, let's look at patients elsewhere and see how they compare. Sarah says if there was any kind of pattern in the type of people that died under his care. Okay, so not just looking at, how many people died, but trying to find patterns within those people. And Tajiri says maybe look at his procedures where people died and see the average mortality rate for each. I agree with all of these. This is great, right? Because now we're thinking a little bit outside the box. I guess in this case, the literal box, which is on your screen. We want to think not just about his patients per se, but how his work compared to the work of other doctors, or how the medication that he prescribed compared to that of others. Those are all very, very, very good points. I agree with all of you. So I'm gonna look more carefully into Sarah's recommendation, right? What kind of people did he murder and when did they die? So the graph above, or the graph that you see here, shows a scatter plot. Now, a scatter plot is a nice little two-dimensional plot, XY plot, where each point has a coordinate, and that coordinate represents its location along the X and the Y axes. So this scatter plot shows the age of, the scatter plot says victim, but in fact, the original data that was studied was actually patient, right? The age of the patient when they died and the year that the patient had died. And we have a little bit of different shadings to represent women and men, respectively. This scatter plot is also includes a bar chart in the top and the right. So you can see on the top and the right of the scatter plot, we have a bar chart. And what the bar chart essentially shows is a frequency distribution. So if we were to look at the bar chart up here, this is a frequency distribution, right, of the number of patients that died per each year. If you look on the right side of your scatter plot, this is a frequency distribution of the age of the victims who died. Okay, so this combination of graphs should allow us to start drawing some conclusions. And I actually already see some in the chat. So Marco says that it looks like he killed mostly older people. And let's not jump into that conclusion. Yeah, let's say looks like mostly his older patients died under his care. It looks like around 70 to 90 years old. Michael says, well, that age range wouldn't really be too uncommon for the average lifespan. And that's correct, right? So while this allows us to see a bit of the pattern of his patients who had died under his care, this is actually not very different from the ages at which people typically die in the UK or died in the UK during those years. So I like that we are starting to draw some conclusions, but I also want to encourage you to think a little bit outside the box and think, well, how does this compare to everything else? Christian notices one important thing. There's a gap around 1990. And Marco notices, but there's a spike in deaths between 1990 and 1995. Okay, good. So we understand, and Ramtin said that he changed the patient's will to get their money. So he did that with one patient, and that's how the investigation started. So that's when he got careless, right? Just with one patient. So none of these had anything to do with wills or with money. These were just patients that died. I like that we're all noticing these little patterns and trends here. We can kind of see that most of the data is more or less cluttered, I would say, in this area, right? Between 1990 and between 1993 and 1998, and between ages of 70 and 90. That's where most of the data is cluttered. And we got to ask ourselves why. Like, why did the patients under his care suddenly start dying at higher rates during this year? And you can see that there are clear gaps. There's a gap in the late 70s, but more uncommonly is this gap in 1992. There's a really, really interesting and very, very uncommon gap. So we will need to bring in some additional data from the outside to try to interpret this graph. Michael brings up a good point. Where he worked would also be important, and that's great. So Michael, let's say that you are the forensic investigator. You decide to figure out where did he work. And guess what? From 1975 to about 1991 or to 1992, he worked in a shared practice. So he had a practice that he shared with other doctors. And it was in 1993 that he started his own private practice. In other words, he worked alone in the 1990s. Now, what does that tell you? Looking at this data, and with the knowledge that he used to work with other doctors for about the first 20 years of this data set, or about the first 15 to 20 years, and then he worked alone for the last 10 years of this data set. Okay, it seems that the deaths of his patients spiked when he started working alone. Now, Renee comes into a little bit of more induction, right? It's harder to murder with others in the office to notice. And that's actually a very good point. Ramtin says that he watched a documentary, and a guy said for these kind of people, killing is like an addiction. So at some point, he might have been fighting his own addiction to kill in those gaps. I would say that that's a good point to bring up, but then that would require a bit of a bit of a psychological analysis, psychiatric analysis, which unfortunately we don't have access to because he refused to speak to anyone regarding the murders. So good to keep in mind as a possibility. However, it's something that we cannot prove. What we can prove is things, objective things like where did he work? And like I said, you can clearly see that the deaths in his patients spiked when he started working alone. Now, we're not really here to answer the question of why, right? We want to answer the question of how many patients he killed. We don't really want to answer the question why, but if we did want to answer that, Renee brings the point that it would have been harder to murder so many people and get away with it with other doctors in the office who could notice that trend. So these are all very, very good points. Renee says, I'd be interested to see if any time of the year was more murdery. I like that adjective. Like, man, it's hot in the summer. These people are going to die. Okay, let's tone it down a little bit. But yeah, that would be an interesting thing to look at, right? Not just the year when they died, but the month or the season within the year that they. Now we're actually going to look at something along those lines, but a little bit more specific. This next graph shows a line graph. And this line graph shows the percentage of deaths compared to the time of the day that these patients died. Now, before I read the messages in the chat, we notice that we're not just looking at Harold Shipman's patients, but we're also comparing it with some average numbers of local doctors, so other doctors in the Manchester area. Now, going back to the comments in the chat, Christian observed that there are more women than men murdered. Yeah, that's true. There are more women than men murdered. That was the darker spots were women, the lighter spots were men. And it's true. The number is actually not as big, but there could be another reason for that, right? We could try to think, why would it be more attractive, right, or more likely for older women to die compared to older men? Now, Tajiri notices from this next graph that the peak death hours for Shipman are actually low points for other doctors. So what's going on here? Well, we see that most of his patients died around, I would say, 3 to 4 p.m. compared to other times in the day. Now, the question we want to ask ourselves is, Michael says shift change, that's something we can think of. One thing I would like to ask myself is, at what time during the day did his patients visit him? And can anybody guess what the answer was? Yep, that's correct. Most of his patients, he actually did after lunch, afternoon calls. In other words, he saw his patients between 1 p.m. and 5 p.m. That's when he saw most of his patients. Unsurprisingly, the times when he saw most of his patients coincide with the times where the majority or the largest percentage of his patients died. You can see that that is not really the case with other or average numbers with local doctors. It's not very common for you to die at a doctor's office, right? Or, you go to a doctor, hey, I have a lump. They find out that something very terrible, you die some days later. But normally you don't die the day that you visit the doctor. So you can see that with other doctors, patients dying during the visit times is actually lower in numbers than than compared to Harold Shipman. So we're starting to see some trends here. Now, based on what we see in this graph, would you say that the 15 patients that he was tried and found guilty of murdering, would you say that they were his only victims? Again, there's no forensic evidence from their bodies to study, okay? It seems that we are doubting it, right? And it seems that we doubt it based on this data, based on these data, right? We see that there are clear patterns that coincide with conditions that would make it more likely. I know I'm throwing in a lot of conditional words there, but there are clear patterns that coincide with conditions that make it more likely for him to have murdered more patients. Things such as the spike in deaths when he started working on his own, things such as the number of deaths that occur during his visits. Those are things that kind of point to us towards an eerie and unfortunate truth that he may have murdered more patients than those he was found guilty of murdering. If we go back to this original graph, Marco had already made some observations regarding the age. Now we see that most of the patients were elderly, between 70 and 90 years old. But Michael also noticed that that's actually a pretty common age for people to die. Now I want you to put yourselves in the shoes of Mr. Shipman. Why would you choose to target victims or potential victims in that age range? Because it is easier to get away with that. It is not uncommon, and it would be easier to prove or to show that those were natural deaths. And that's exactly what he was doing, right? He was showing that they had died of their illnesses. Tajiri brings up a good point. Their deaths would have seemed more likely due to their age group, and that's correct, right? You see general death statistics, and you'll see that most of the people that die are within that age range, 70 to 90 years old. More people die within that age range than, let's say, 100 years old because, well, not many people actually make it to 100 years old, right? So they're more likely to die of natural causes, says Marco. And Renee says that it could be that he didn't even start murdering until he had his own office. Those priors could be normal deaths. I think the time of day graph should be two graphs, one from his previous practice and one from his solo practice. And those are all very, very good points. So we can see now how the data we have, while helpful, is not sufficient, right? We want to know, first of all, not just of how Harold Shipman's numbers look like in this scatter plot, but also what other numbers from other doctors would look like. And then we also want to know regarding this second graph, not just about all his patients, but we would like to know about the percentages of death during his first shared practice and during his tenure in a private practice. So these are all very, very, very good points to make. These are all very, very good observations, and you may not realize it, but you are already taking on the role of a descriptive statistician, because you're already realizing not just how to interpret the data, but what other data to present or to find in order to understand whatever it is you are studying. So I would like to commend you for that. You're doing a great job. And I'm sure that being a forensic investigator is going to be very helpful for your future careers as civil engineers. I'm joking, by the way. All right, so we see that the age of the patients seems to have been purposely chosen because it does seem to align with the ages at which people die. The pool consisted of men and women, but there's a slightly larger number of women who died under his care. Now, we don't really have enough of a difference to figure out why this larger number of women existed, but we can always speculate. So deaths of his patients have occurred since 1975. Most of the deaths occurred between the years of 1993 and 1998, which Marco had already noted. And unlike other local doctors, a significant percentage of deaths of patients under Shipman's care occurred between 3 and 4 p.m. So all this information that we have drawn just from these two graphs allows us to put together some conclusions. Now, of course, the real analysis took years and, well, a few years. And it consisted of gathering much, much, much more data. But notice how much we were able to deduce only with these two graphs. We all agree that we need more data to come up with definite conclusions, which the forensic investigators did procure. But only with these two graphs, we were able to come up with several key observations of Harold Shipman's modus operandi and his general patterns and his just his thought process or his work process. Okay, that is the field of descriptive statistics in a nutshell, and that's why I love this field, because it allows us to think. Notice that we barely use numbers here. It allows us to think in a very graphical and very visual way. Now, you know that I like the graphical approach a lot more. I like geometry over algebra. I like, comic books over reading. No, that's actually not true. I love reading, but I appreciate books with illustrations. So I'm definitely more of a visual or graphical person. And that's why I enjoy this field, because it allows us to draw conclusions, to analyze data, to interpret data using more of a visual and graphical approach and less of a numerical approach. So what we're going to do today is talk about the different methods or the different ways that we can visualize data. Now, we're not going to go over an exhaustive list of every single data visualization tool or method out there. Instead, we're only going to focus on 2 or 3 that are common to the field of civil engineering and to other engineering fields in general. Now, I'm going to start with a dot diagram. A dot diagram is essentially a visual display of a stem and leaf table. So you may remember in the last class, I taught you how to make a stem and leaf table, which was just a little table that organized all of your values into stems and leaves. Now, I don't have to go over this explanation again today, but how that relates to the dot diagram is it allows us, instead of actually writing down the numbers, right? The numbers that you would find in a stem and leaf diagram, a stem and leaf table, the dot diagram only uses dots. What we have here is a dot diagram of pull-off force measurements. And these were actually the same measurements that we found in the stem and leaf table that we drew in the last class. So if you go back to your notes from last week, you'll notice that you had a stem and leaf diagram. Now this dot diagram consists of the same data that you used in your stem and leaf diagram. Notice that all we have to do for a dot diagram is plot our range in one axis and then insert a dot at the location of a specific point. If a data point appears more than once in your set, then you just have to stack the dots on top of each other. What we have here is that there is one data point that appears more than once. If I remember correctly, it was 12.6 in our data set, and therefore we have 2 dots that are stacked up in this dot diagram. Our dot diagram is a very, very simple form of visualization. In fact, it's so simple that it shows up in the very, very first pages of your textbook. It's very easy to understand, very easy to look at. And of course, with more data sets, with larger sets of data, it will be easier to use to determine and deduce patterns. So that is the dot diagram. It's essentially a visual display of the stem and leaf diagram. And it represents each observation as a dot on our range, our real number line, which represents the range. And it allows us to stack repeat observations on top of each other. Of course, we do this so that we can clearly see when values are repeated in this dot diagram. We are going to look at the dot diagram from here on to the rest of, to the end of the semester. It's nothing, there's no complex way of drawing dot diagrams. So I would, not really spend too much time talking about it or explaining it. If you want to get some practice, you can take the data from your stem and leaf table from the previous class and plot that in a dot diagram, and it should look exactly like the one you have on your screen. The next type of visualization tool that I would like to talk about is called a histogram. Now, a diagram was a visual display of a stem and leaf table. In contrast, a histogram is going to be a visual display of a frequency distribution. You may recall in the last class, right before the end of class, we talked about how to create a frequency distribution. Now, the difference between a dot diagram and a histogram or a frequency distribution is that dot diagrams plot individual points, whereas frequency distributions instead tend to plot ranges, amounts of data points within a range of points. So whereas your dot diagram had individual points, the frequency distribution has the number of recurrences, the number of occurrences in a range of points. Before we finished our last class, we started but did not finish an example from the textbook where we had a set of 80 data points and we wanted to organize them in a frequency distribution. For our table, we divided our numbers, our range, into bins of about 20. So for our first bin, we decided to count the number of elements that were between 70 and 90. And that's the number that you see plotted here. The number of elements between 90 and 110, and that's the number that you see plotted here. So you can see that whereas a dot diagram looks at individual points, a histogram looks at points in a range. Now, depending on how much data you have, histograms may be more useful than dot diagrams because since histograms focus on a range, it allows us to see a clearer pattern in the general measurements. In this case, it was a compressive strength measurement. So it allows us to see the clearer pattern that exists in physical measurements. What is the disadvantage of trying to use a dot diagram with this data set? Since the dot diagram looks at individual points, if it turns out that no point was repeated across this entire range, then we could actually end up having a horizontal line with just dots across the entire line, unless a point or points were repeated. With the histogram, we don't have to worry about that because we're looking at ranges, then we're just counting, right, the number of points that accumulate within that range. So even though we have a point 153 and another point 165, because they are in the same range, they are part of the same. This is what we call a histogram. Very helpful form of presenting data. What we have here is on the y-axis is the frequency, and the frequency corresponds to the number of occurrences. We can see here that measurements between 150 and 170 occurred more than 20 times. So there are more than 20 measurements within this range. Compare that to the measurements in other ranges, and you can see that this follows almost, not entirely, not completely accurate, but it slightly seems to follow a symmetric or normal distribution. In fact, if we were to rearrange the bins just a little bit so that instead of dividing data in terms of 20, we divided it in other numbers, then we would probably be able to arrive at a more normal or bell curve looking distribution. This axis in the far left is the relative frequency. Now, whereas the frequency looks at number of occurrences, sometimes the number of an occurrence doesn't say anything. I can say, without showing you this graph, I can tell you there were 15 measurements between 130 and 150. But what does that tell you? that just says that there were 15 measurements between 130 and 150. That doesn't mean anything. However, if we were to take the observations, this frequency, and look at it relative to the total number of observations, then we would land at what's called a relative frequency. In other words, these points in the relative frequency are formed by taking the number of observations and dividing it by the total number of observations. In other words, the total number of measurements was 80. So what we'll have here is 25 divided by 80, which represents about 31% of the entire data set. So whereas I can say there were 15 observations between 130 and 150, that doesn't really tell you anything. But instead, I could say 19% of our observations are between 130 and 150, and that is a lot more a lot more helpful because it allows us to see your observations relative to your experiment. I can say that more than 25% of observations were between 150 and 170. So that shows you that this bar alone already counts for more than a quarter of all of these measurements. So using a relative frequency does allow us to understand our measurements, our observations, a little bit better. It is a little bit more self-contained and allows us to draw conclusions without necessarily needing every single data point. Notice that with the relative frequency, we don't necessarily need to know the number of observations or the total number of measurements, right? Because the relative frequency already combines all that and already shows us all of these aspects of the project. Our frequency can be plotted into a histogram like what we have on the screen, but we could also try to plot it as a cumulative histogram. So a histogram with a cumulative frequency. So when I say cumulative frequency, what I mean is that each bin, right, each bin will contain not only the observations in that range, but also all the observations before that range. So what we can see here is a cumulative frequency, where the highest range, the range of almost 250, the highest numbers, includes all of the observations in that range, and to that it adds all the observations in the previous range. Now, because there were 80 total measurements, that means that the highest value here will have a cumulative frequency of 80 because it includes all of our measurements. Now, the cumulative frequency, even though it doesn't give us this nice symmetric curve that we are used to seeing, it does point to us the growth in our data sets. Now you can see that the growth of our data is actually less at the beginning and at the end of the data. That represents our extremes or outliers, but we have far more growth near the middle of our data set. And you can actually see that the rate of growth for pretty much the half, for pretty much 150 to almost 200, that rate of growth is relatively the same. So the cumulative frequency allows us to assess the growth in a data set, whereas a traditional histogram with a traditional frequency distribution does allow us to see the central values, the values towards which our data will tend. I can't say that one of these graphs is more helpful than the other. It really depends on what it is we are trying to understand, what we're trying to see. So that is a histogram. It's one of the graphing methods we're going to be using in this class. I would recommend that you learn how to create histograms because you know that we're going to be dealing with larger data sets, and we've already started slightly, right, dealing with somewhat larger data sets in our in-class problem. And while we're dealing with larger data sets, it's going to be very important, right, for us to be able to automate our numbers and to understand what's going on. So I would recommend that you all learn how to draw a histogram in Excel, so that when I give you a data set and I ask you to analyze the data, all you have to do is click a few buttons and you'll have your histogram all nice, all set up for you to view and analyze. Now I'd like to move up to my favorite data visualization method. It's my favorite. It's the one that I use the most because it doesn't require multiple variables in order to make sense. It can be used with just one variable, multiple observations of the same phenomenon. In the biological sciences, where I am currently doing research, it is a very, very common tool that is used. And I've come to appreciate it because it has helped me do things like look at my grades and my students' grades and more or less put them into perspective. This next visualization method is called the box plot. Now you see this, you're already thinking, wait, there's a lot of numbers, there's a lot of things in there I need to think about, but it's okay. We're gonna explain what each element in this box plot represents. And you'll see the usefulness of a box plot. Now for me, a box plot is very, very, very useful because it combines both a visual and a numeric approach to our data. And that's something that is very, very important to me, the combination of visual and numerical approach. A box plot essentially organizes your data and then divides it into quartiles. Now, we will want to explain, right, a little bit of what all these things mean. So let's try to review some of the material from last week's content. Let's remember that we talked about organizing our observations. We said that if we organized our observations in ascending number, we could find the median by selecting the middle value. And if there was no single middle value, we could find the median by averaging the two middle values. That was the median. What the median does is it splits our data into two equal halves. In other words, the median is going to have the same number of data points above it as below it. That's what the median is about. But we also talked about dividing our data further. If instead of dividing our data into two equal halves, if we instead divided our data into 4 parts, right, into 4 quarters of equal size, then the point of division is called a quartile. So we talked about it last week, but we said that the first quartile is the number that is above 25% of your data and below 75% of your data. The second quartile is a number that is above 50% of your data and below 50% of your data. And the third quartile is above 75% of your data and below 25% of your data. Now, based on this definition, how do my quartiles relate to my median? Any ideas? How do my quartiles, or one of my quartiles, relate to the median? That's right, Carlos. The second quartile is the median because both numbers have half of your values above it and half of your values below it. So the second quartile and the median are actually going to be the same number. So a box plot shows all of this. I would like to walk you through the different elements of a box plot. The box plot shows the first quartile of your data set, which you can see is the bottom of my box. The bottom of the box lies at the first quartile of my data points. And if you are curious, this is the same data that we have used in the previous histogram example and that we used in the frequency distribution example for last class. So it's still the same data. We're using the same different methods to present the same data. So my box plot shows the first quartile, which is the bottom of my box. It shows the third quartile, which is the top of my box. So we call it a box plot because this box essentially covers data from the first quartile to the third quartile. The median is also identified with a straight line that is located inside my box. Now, general question for you all. How many data points or how much percentage of the data points is included inside my box? You took several measurements. Christian says 50%. Let's think about that, 50%, because you can see that 25% of your data set is below the box and 25% of your data set is above the box. So Christian is correct, right? Inside the box, we have 2 full quartiles, which means that we have 50% of our data set. So you may want to take some notes here. One of the important things for a box plot is that the box will include the central 50% of your data. And I say central because there will be the same number of measurements outside the box above it as below it. So this 50% is actually the central 50% of your data. Interestingly, we can see that even though our data ranges from 76 all the way to 245, 50% of those measurements are actually within the range of a little bit less than 150 and about 180, right? So we can see that 50% of the data set is actually included in a range of about 40, whereas my entire data set has a much larger range of about 160, I would say. So it's very useful to use a box plot because the size of this box gives us some insight into how the data is dispersed. If this box is big, very, very big, then what this tells me is that 50% of my data is scattered, right? It's very scattered. But the smaller the box is, then the more confident I can be about the numbers I am looking at, right? Because I can say, well, it looks like half of our measurements seem to want to tend much more closely towards a central value. So a box plot consists of a box, and that box includes 50% of your data. But now let's talk about what's outside the box. This line that extends from the top here all the way to the bottom here is called a whisker. In fact, this plot in your textbook is called a box and whisker plot. But all box plots, not all box plots have whiskers. So I just call it, well, I'm sorry, all box plots have a whisker. So I just call it a box plot because it'd be redundant, right, to just call it box and whisker plot. So what this whisker represents is the minimum and the maximum points in my data set, excluding outliers. Now, when you hear the word outlier, what does that make you think of? What is an outlier in your own view? Okay, I have three answers, and those are good, right? A stray data point that doesn't really match the rest of the data, or a point that doesn't fit in with the rest of the points, or something that lies outside, or a piece of data that stands out against the rest of the data. That's all correct, right? An outlier is a value that stands out, right? That doesn't seem to be within my typical measurements. So what the whisker will do is it's going to identify what is the lowest, the minimum non-outlier points, and the whisker will extend towards the maximum non-outlier points. Now, this whisker itself gives us a visual representation of where your data is located, where the majority of your data is located compared to the rest of your data. You can see that if the whisker is bigger on one side, then your data collection isn't really very symmetric, right? If your whisker is larger on one side, that means that most of your data is actually not tending towards the middle value of the minimum and maximum, so towards the center of your range. And this is very important because even though physical measurements will most likely tend to follow a normal distribution, that doesn't always mean that your median is going to be at the center of your range. Just because it is this middle point in your observations doesn't mean it's the middle point in your range. And we're going to talk a bit about that later today. So this whisker shows us the range of my data from the minimum point to the maximum point. Now you may be wondering, how do we determine what an outlier is? There's actually a reasoning, a methodology that we use to determine these outliers. So first, let me walk you through the procedure for creating a box diagram. I'm just going to try to be as general as possible, but then later we're going to try to draw this or construct this same box diagram in a sheet of paper together so that we can get some practice. Now, I'm going to give you a heads up. We will have an in-class problem that's going to be related to drawing or putting together calculations for a box diagram. So you may want to prepare a piece of paper, a sheet of paper, or maybe a Word document so that you can upload it later today. This will not be due immediately after class. I'm going to give you some extra time so that if you write it down, then you have time to take photos and upload it. When I am going to create a box diagram, the first thing I'm going to have to do is to arrange my data in ascending order. It's always important to arrange your data in ascending order, from smallest to largest, or largest to smallest. You can do descending if you want, but it's important to note that the quartiles start in ascending order. Once you have arranged your data, you are going to want to divide your data into 4 equal parts. In other words, you want to find out what the quartiles are. And you do it by dividing your data into 4 equal parts and determining your 3 quartiles. Your first quartile, Q1, your second quartile, which is also the median, Q2, and the third quartile. Once you have divided your data, you are going to figure out what the interquartile range is. So you can see in this graph that this IQR corresponds to the entire length of the box. So the size of the box is what we call the interquartile range, the inner quartile range. Looking at this graph and noting that the interquartile range is simply the size of the box, then we can deduce that the IQR, the interquartile range, is simply equal to the third quartile minus the first quartile, and that will give me the range of this box. So you organize your data, you divide it into 4 equal parts, figure out Q1, Q2, Q3, and then calculate your interquartile range, which is the distance between Q1 and Q3. With that interquartile range, then you can begin drawing your box. Your box will extend from the first quartile all the way to the third quartile and will have a length equal to your interquartile range. You also want to draw a line representing your median or second quartile, which will be inside that box. So how do we determine the length of the whisker? here's where we have to be careful in selecting what an outlier is and what an outlier isn't. What we are going to do is we are going to define any point that is further away from 1.5 times the interquartile range as an outlier. In other words, take your interquartile range, multiply it by 1.5, and then add that number, add that value above your box and subtract it here below your box. Any numbers that fall within this range, so from 1.5 times the interquartile range above your data set to 1.5 times the interquartile range below your data set, any values are fair game, right? They will be part of the whisker. So your whisker is going to extend within that range to the highest in the case of the whisker above and to the lowest in the case of the whisker below, values that are within this range of 1.5 IQR. You can see here that 1.5 RQR, 1.5 times the interquartile range, 1.5 IQR, is actually very close to the maximum value allowed by the whisker. But down here, we can see that 1.5 IQR is actually kind of far away from the nearest or lowest value allowed by the whisker. So what this tells us is that we had 97, we had 87. 87 is actually away outside of this range, so it cannot be part of the whisker. The whisker can only extend all the way down to 97. And this is good because it allows us to note this difference in whisker size. That's why it's very important to note, right? To note what the maximum and minimum points in your data set are, so you can see the whisker size more effectively. Any point outside of this range is called an outlier, and they are usually represented with these little dots, individual dots. So you can see we have an upper outlier here of 245 and two lower outliers here. Now this data set doesn't necessarily include them, but we actually have a second type of outlier called an extreme outlier. Extreme outliers are those that fall outside of 3 times the interquartile range. In other words, if you take 1.5 IQR and then you double it, anything that falls outside of that range, above and below, is an extreme outlier. Those are also identified individually. However, sometimes you may want to identify them differently, so in a different style or a different color, or in some cases, you may even want to exclude them from your data set. Now, the inclusion and exclusion of outliers is something that we want to be very careful with. In fact, in today's class, we are focusing on how to calculate your outliers, but I am not making or taking any decisions. I'm not making any decisions regarding their exclusion or inclusion. So we will, by default, include the outliers in our data set when calculating numerical measures such as mean and median. So that is a box plot. We are actually going to construct this, so don't worry if I was running a little bit too fast. We're going to have some time to work on this box plot. It's a little bit early for the break, but because we want to take some time, it's going to be a significant amount of time to study or prepare our box plot. Let's take our break early today, and we will meet back at 3:20. So take a break. We'll meet back in 15 minutes or 13 minutes. We'll start again at 3:20. Make sure you're back on time and make sure that you have a sheet of paper or your laptop so that you can start solving this problem, which we will collect today.